My name is Jiao He. I'm from Max Planck Institute for Astronomy. I'm going to talk about phase transition of interstellar sea ice and the formation of complex organic molecules. So, dense molecular cloud is the place where many complex organic molecules are formed and also identified in space. And if this comes somehow survives the star formation cycle, then they may be delivered to the solar system and the planets like the Earth, so that forms the basis of the origins of life. So my talk will mostly focus on how the comets are formed, the mechanism of their formation. So we know that the complex organic molecules are mostly formed in the solid state on top of the cosmic dust grain surface. So here is the cartoon of the dust grain surface, and it roughly consists of two layers. The inner layer is dominated by water in the amorphous form, and the outer layer is dominated by CO, but also contains some other molecules like formaldehyde, methanol, and maybe also other complex organic molecules. It's already known that the CO-rich layer is probably the most important place to form COMs. Methanol is particularly important. So it is the simplest and the most abundant COM in space. And it is formed from hydrogenation of CO. So that's why it is in CO-rich environment. And along the formation route, so you can see that there is HCO and the CH3O, CH2OH radicals produced along the way. And the recombination of these radicals, they can produce even more complex species. Methanol is probably the most important starting material for conformation in ISM because the dissociation of methanol can produce radicals like HCO, CH3, OH radical, and then they can recombine in a solid state to form larger species. So I just said the CO-rich layer is very important for conformation. Now let's talk about the mechanism of conformation. So basically there are two types of reactions in the CO-rich layer. One is thermal reactions, and basically we don't have UV or cosmic ray. We start from simple atoms and molecules. So thermal reactions is mostly responsible for the formation of simple molecules. And then after the formation of the ice, and then the irradiation chemistry take place, and it's responsible for the formation of even larger COMs. So here on the right side, it shows just an example of how complicated the chemistry can be, even starting from the simple material like CO and hydrogen. And this is mostly studied in Leiden Observatory and also by Nelke's group. This is another example. So this shows the irradiation chemistry in the CO-rich layer. So starting from the CO and the methanol ice mixture, and we can see that a lot of chemistry can happen. So this is very complicated. And the real situation could be even more complicated than this one. So it's only limited by the detection sensitivity. So this is the study by Ralph Kaiser's group. So we know that a lot of COMs can be formed in the CO-rich layer. Then there is one question. We know that radicals, they need to recombine. And then in order to recombine, they have to diffuse, or they have to somehow come together. Otherwise, they cannot react. So it's already known that diffusion is not efficient at 10 Kelvin or below, with the exception of hydrogen. And diffusion in bulk ice is even more challenging. So non-diffusive mechanisms have to be involved. There are some people propose non-diffusive mechanisms, such as Garrett et al. So they propose that maybe it is the case that radicals, they happen to sit next to each other, and then they don't need to move around. So the question is, what is the chance that the radicals sit next to each other? And maybe there are some radicals they do not sit next to each other. Then how do they recombine? So I'm trying to address this issue in this work. The other question is, what is the morphology of the CO ice? So we know that the inner layer is dominated by amorphous water. How about CO? Is it amorphous or crystalline? So experiments in this study, we have 3 sets of experiments. The first is this pure CO on amorphous solid water, and we try to study the phase transition temperature. And then the second is CO and the CO2 ice mixture. So we try to dope a small fraction of CO2 in the CO ice and see what is the impact of the impurity in the phase transition. And then in the third set experiment, we try to have some methanol in CO, and we shine it with UV radiation and look at how does the phase transition affect the chemistry in the ice. So the experiment number 1 and number 2, they are performed in Heidelberg, and the third one was performed in Budapest. So in both cases, after the ice condensation on cold substrate, we use infrared spectrometer in the reflection mode to monitor the ice composition. And since Shandor has already introduced the setup, so I'm not repeating it here. And I want to point out one key factor here, which is the temperature. The lowest temperature can reach 3 Kelvin. So without this low temperature, it couldn't be done. Okay, so this is the result of the first experiment. After the condensation, we can see that, So after condensation, we warm out the ice. So with 2 molar of CO on the amorphous solid water, we can see that there is a phase transition clearly at 17 Kelvin. If the thickness goes to 11 molar, the phase transition temperature becomes 8 Kelvin. So clearly, there is a temperature dependence. And on the right side figure, it shows how does the phase transition temperature depend on the CO ice thickness. And it's important to note that the phase transition temperature happens around 10 Kelvin or sometimes below 10 Kelvin, depending on the thickness. And this is the temperature, this temperature coincides with the molecular cloud temperature. So we know that phase transition of CO should be important in molecular cloud. So in a second set of experiment, we doped 10% of CO2 in ice mixture. The total thickness was 10 molar. And then here we see the same thing. There is phase transition at about 9 Kelvin. And we can see from both the infrared for CO2 and CO. If we compare this temperature with the pure CO case, we can see that they happen to be at more or less the same temperature. So one conclusion is that if we have a small fraction of CO2 in the CO ice, there's not much change in the phase transition temperature. And then the second thing we should look at is, so here, the CO2, so before the phase transition, this is at 2345, which indicates isolated CO2 molecules. And after the phase transition, this band indicates the formation of CO2 clusters. So we know the CO2 should form clusters during the phase transition. Then the next question to ask is, what if the impurity in the CO matrix is not CO2, but rather some reactive species? And then they should also form clusters, and then they should react with each other. And this is what we try to verify in the third set of experiment. Okay, so this is also a continuation of the second set of experiments. So based on the CO2 and the CO ice mixture, we did a whole set of isotherm experiment at different temperatures, and then we try to study the kinetics. We study how does the phase transition depend on temperature and the time. So basically, we get the kinetics information that is shown in this part. So we get some numbers that may be useful in models to describe, to quantify the phase transition of a CO. Yeah, so we know the temperature dependence, time dependence, and the thickness dependence. Then we can put all three together in a model to predict the morphology of CO in a dense molecular cloud. So I'm not going to get into details, but the conclusion is that within the lifespan of a typical molecular cloud of 10 to the 5th years, almost all of the CO ice should become crystalline, unless the CO is too thin, let's say less than 1 molar. A similar conclusion a similar result has been obtained by Naoki's group, and they also predict that CO should be mostly crystalline. Okay, so this is the third set of experiment. So we have 7% of methanol mixed in CO, and the total thickness was 500 molar, and then we have half an hour of UV radiation to produce radicals. So the inverse spectrum is shown here. So the red curve shows the ice right after the deposition at 3 Kelvin. So it's important to notice 3 Kelvin. Here we can see the methanol features, and this is the CO, including 13 CO features. And then the blue curve, the green curve shows the one after UV irradiation. So new species are formed, such as CO2, HCO, and H2CO. And then we warm up the ice to 5.3 Kelvin. Sorry, that's not working very well. Sorry, okay. So as you can see that in the methanol feature, there is a very sudden change, a very dramatic change, I would say, between 3 and 5 Kelvin. So that indicates a phase transition of CO between 3 and 5 Kelvin. And there are also other changes. So now let's look at the, okay, I just should explain here. Sorry, this does not work. Oh, okay, here. So as you can see that when the phase transition happens, the HCO also decreases to a very small value. So that means most of the HCO, they are consumed during the phase transition. Okay, so on the left side figure, we show the integrated band area of HCO and H2CO. So we can see that at 4 Kelvin, HCO drops and then they go to H2CO. So this indicates that 2 HCO radicals, they react in the forms of H2CO and CO. On the right side, it shows the CH2OH, and it's the same story. So although it's a small peak, but definitely there is some CH2OH produced, and then they also consumed when the phase transition happens. So we know that radicals should recombine when the phase transition happens. So here I would like to propose the mechanism to form COMs in the ice mantle. So we start from amorphous CO and with some impurities, and including some radicals, and then so as the ice becomes thicker and thicker, it becomes easier and easier to make a phase transition. And at a certain point, all of a sudden, it becomes crystalline, and then radicals, they should recombine to form complex species when the phase transition happens. And this should be an important mechanism, non-diffusive mechanism to form COMs. So a similar thing has been observed in water. So this group by Guddipati, they found that PAH also form clusters when water undergoes a phase transition. So the next question is, what about the phase transition of other ices? So that is something has to be studied further. Okay, I would like to propose some future studies. A more systematic study on the CO phase transition is still necessary, and one should also look into how does what is the impact of irradiation on the phase transition. And of course, we need to study the phase transition of other molecules like N2, O2, methane, etc. I also want to point out that in laboratory astrochemistry, in ice chemistry, it is important to consider the role of phase transition. So we know that with or without phase transition, the chemistry is going to be very different. And also, the infrared spectrum would also be very different between these two cases. So one has to take this into account. From the modeling side, one can use like molecular dynamics to simulate the phase transition of various molecules, and it's also a good idea to incorporate phase transition in astrochemical models to predict the formation of COMs in space. With this, I would like to conclude my talk. Thank you.
Thank you very much, Zhao. Stefan, first question for you.
How many CO molecules do you think you need for the phase transition? 10?
Okay. You mean how many molecules, or do you mean molar layers? Oh, okay. How many molecules? I don't know. I don't know. Honestly, I don't know. So our infrared spectrometer has sensitivity limit. So we could only measure like let's say 0.1 molar layer. So that's the detection limit. Yeah. So if the coverage is too low, so probably we're not going to see the formation of crystalline CO. That's my impression.
And maybe it doesn't show phase transition if it's too small.
I'm not sure. Maybe. Yeah.
Just go ahead.
So I have some comment which is related to the Stefan's questions. So many people believe that the CO molecule can cover at the cover of unity on the water ice, I mean the ice dust, but that is not true. So we observed directly by TEM, transmission electron microscopy. So the CO can move very quickly, even at 10K, easily segregated to form an island. So in that case, CO can be some solid phase, not smooth layers. So we can recognize this is crystalline or amorphous phase, even at the amount of the monolayer solid, monolayer amount of the monolayer. But that is actually not a monolayer. This is some bulk on ice surface. And in that case, we believe the hydrogenation of CO should be considered not only the solid CO, but also the boundary of between the solid CO and the water ice, because the hydrogen can move very quickly on the solid CO and can meet the boundary between the CO and the layer, under layer water ice. So we need to consider the CO diffusion not only in the solid phase, but also the water ice interaction.
I would like to follow up on that. So basically, this boiled down to a question: does CO wet amorphous solid water? It's the wettability, and according to my infrared and TBD studies, and my results indicates that CO can wet the surface. They do not form clusters. But your result shows otherwise. I think we should have a discussion about that later.
Yeah. So I know your paper, and I know many reports, but we did a direct observation. That is not information from the spectroscopy. We observed directly by TEM, so we believe our result.
All right, time for final question. And I go there. Rolf, you have so many questions, so you're next.
Thank you. Previous studies have shown that below 70 Kelvin, you can cause a crystalline water ice to amorphize as a result of its UV irradiation. But a couple of years ago, papers have shown that this is not the case with carbon dioxide ice, that it never undergoes amorphization as a result of its irradiation. Have you considered whether the phase change back to an amorphous ice could be induced in CO, in a pure CO ice via its irradiation?
I think it's possible. So by definition, crystalline ice has a long-range order. So let's say you have irradiation, cosmic ray, whatever. It can produce some radicals inside the ice and then make it break the long-range order. So I think it's possible. And actually, this is a very good point. So what's happening in space may be that so there is a continuous transition from amorphous to crystalline, and then from crystalline to amorphous. So it goes like cycles. And then whenever the phase transition happens, there is chemistry happening, forming more comps.
Thank you.
Ralph, is it a short question?
Yeah.
Then please go ahead.
Thanks for that. Yeah, very quick question. On the graph that you had a little while ago where you, I think you showed spectra at, was it 4 Kelvin and then raised to 5 Kelvin or 3 Kelvin to 4, I can't remember. Did you reduce the temperature back down to the lower temperature afterwards and take a look at those results?
I think you're asking whether the transition is reversible. It's not.
Short answer, perfect. Ralph, you're the really last one today. Yeah.
Just one comment and one question. You are at Max Planck Institute with almost unlimited funding of your supervisor. Why do you still do broadband irradiation of photolysis and not single wavelengths, which is, gives more information? Second question, you define it as a phase transition. I think this is based on physical chemistry, fundamental knowledge. This is not a phase transition. A phase transition is well defined for CO. You have an alpha phase, a beta phase. What you have there, it's neither of them. So you shouldn't call it phase transition. Maybe in APJ for publication, yes, but when it goes to JCP, it will not pass under phase transition. It might be a good idea to look for another word, how you describe it.
First point, our institute does not have limited funding. So the second thing, I kind of agree with you. So I also I was struggling with the terminology. How do we call it? And after some discussion with co-authors, we say, okay, this is a phase transition. So maybe it's more appropriate to say that it is a formation of a longer range order. I'm not sure.
Session. So thank you very much, Zhao. Thank you all speakers. And enjoy your break.